Okay, this is the final video in this topic of forces. And what I'm going to talk about here is the concept of friction. We're going to talk about different kinds of friction, static and dynamic, static and kinetic. These are really important. Again, you've been dealing with friction in virtually everything you've ever done in your entire life, and now it's time to kind of quantify it and to understand how friction works from a physics point of view, okay? Friction occurs when an object moves or attempts to move along a surface. This frictional force is always parallel to the surface, okay? Sometimes we want friction, like in the case of pistons in an engine. That's why we put oil in to lubricate the pistons. Oil reduces the friction inside of an engine, okay? And that's also why the engine gets hot, is because the oil doesn't do a perfect job, and friction creates heat because it's dissipated energy, okay? Other times we don't. For example, tires on a road. The rubber increases the friction. So there's what's called the coefficient of friction between the rubber and the tarmac. And we want that to be really, really big. That's why driving in the rain and snow is dangerous, because what that does is that actually reduces the coefficient of friction between the rubber and the surface. So we'll talk a little bit more about coefficients of friction later on in this video, okay? Now, on a molecular level, if you're looking at, say, two books sliding over one another, okay, what happens is you're actually getting the atoms in motion, and as they're in motion, they get agitated, they move around, they vibrate more, and what this means on a molecular level is that the temperature goes up, okay? Now, the harder they're pushed together, the more heat that's generated. It's very easy to imagine. Like if you rub your hands together, but push them together really, 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 really hard, your hands will actually feel like they're getting hotter, okay? The harder they're pushed, the greater the normal force, okay? The greater the normal force between those two surfaces. So it must be that the frictional force is somehow proportional to the normal force, okay? And we're going to talk about that, all right? Static friction is the first kind of friction I want to talk about. And this is friction. This is the horizontal force that keeps an object from moving when a force is applied to it. There's no relative motion between the two objects in contact. Static friction is denoted by a little f sub s vector, okay? And it's given by this equation. It turns out that static friction is a variable kind of friction, and it varies between 0 and a maximum value, but it's always given by mu sub s, okay, which is called the coefficient of static friction times the normal force. And I'll explain why static friction is between 0 and this maximum value in just a little bit, okay? So again, if the box is not moving but I'm applying a force to it, F equals F sub s, okay? If I apply more force to it and the box is still not moving, then clearly this vector has gotten longer, but then this vector has also gotten longer. If I apply so much force to it that the box just starts to move, then that's the maximum value of its kinetic static frictional force, and then it will start to move. And in that case, the kinetic frictional force takes place, okay? Again, static frictional force varies from 0 newtons to a maximum. As force is applied, so does F sub s. The maximum F sub s is just when it starts to move. F sub x is directly proportional to the weight of the object, since W equals Fm. This makes sense because the harder the block is pushing on the tabletop, the more force would be required to pull it and get it moving. Okay? All right? Now I should point out what's interesting is that the orientation of the object does not matter. Notice that in this equation there's nothing saying anything talking about the surface area whatsoever. Okay? So whether it's on its end, big end, small end, whatever, it doesn't matter. It's the same situation with static friction, okay? So again, static friction, the maximum static friction is going to be a case where F sub s equals mu sub s equals the normal times the normal force, where mu sub s is the coefficient of static friction. So in the case of this cute little dog standing on this dog ramp, okay, we have that. In this case, the x component, the horizontal component, the component of the weight parallel to the ramp, think of the inclined plane, is exactly equal in magnitude to the static frictional force acting upwards, okay? And by that measure, the vertical component of the dog's weight is exactly equal in magnitude to the normal force. So when you're trying to figure out the static frictional force, you want to use this normal force, which is the y component of the weight, and of course the dog's weight is acting straight downwards, okay? Now, kinetic friction, F sub k, this is the horizontal force exerted between two objects when one or both of them is moving. It's called dynamic friction, and it deals with relative motion. And this is actually simpler than the case of static friction because kinetic friction remains a constant, and it's equal to mu sub k times the normal force, where mu sub k is called the coefficient of kinetic friction, okay? So here's a case where some kids are sliding down the stairway on cardboard, okay? There's lots of friction going on between the plastic snow sled and the cardboard, okay? In this case, there's a different friction happening than the case of the dog stationary on the ramp, okay? Note again that f sub s is variable, f sub k is constant, and f sub k only exists when the object is moving. You may have noticed that to get a stationary object moving requires more force than it does to keep it moving, and that's because the coefficients of static and kinetic friction are different. Note that in every case, you might want to pause the video and actually study these values. In every case, the value of kinetic friction, the coefficient of kinetic friction, mu sub k, is less than it is for the static friction. And this means that kinetic frictional forces are always less than static frictional forces, which is a way of quantifying the above statement right here that I'm highlighting in red here. So to get a stationary object moving requires more force than it does to keep it moving, okay? You want to be aware also of the differences of the equations given in your data booklet and what I'm giving you here. This is what your data booklet gives you, and this is what I'm giving you, okay? The IB calls the normal force R, and instead of static and kinetic, it's static and dynamic, and they're calling the force of friction big F sub F, which I think is confusing. Okay, I prefer my nomenclature to the IB's, but just be aware that this is what you'll be given in a testing situation. Okay, so examples of friction are everywhere. For example, rock climbing. If you've ever gone rock climbing, without static friction would not be possible, would be super dangerous, and everybody would die. Nobody would do it because they would just slide right down the rock. Okay, that's why rock climbing is very dangerous when it's raining or when there's ice on the rock. Okay, driving without static friction would be very dangerous. Okay, so again, here's a wet road, and the tire, the kinetic friction between the tire and the road is what slows the car down to a stop. Okay. And in the most extreme case, when it's super icy, okay, you know, this white car has got inertia, so it's got momentum, but the street is so slick that the car is not able to stop. So the tires are not able to actually provide that frictional force to stop the car. And this is why tires have what's called the tread. It's because the way the tread is set up, it actually seeps away the rain and the snow from the middle of the tire. It actually goes through in these channels, which actually maximizes the friction between the tire and the road. So pretty neat invention, the tire, okay? So putting it all together can be fairly complicated. Please pause the video, spend a few minutes reading this example very, very carefully before I go through the solution. Okay, so basically this is an age-old question of, by Newton's third law, okay, and this is Newton's third law, even though this is the friction video. By Newton's third law, if I push on something, it pushes back on me, so nothing should ever really move. Well, this reasoning is faulty. This is ridiculous, okay? Action and reaction forces are always exerted on different objects in this case, okay? So there are two forces that affect the assistant's motion in this case, okay? F sub AG, okay, which is the force on the assistant exerted by the ground, which is right here, okay? And F sub AS, which is the force on the assistant exerted by the sled right here. As long as F sub AG is greater than F sub AS, the whole thing is going to accelerate forwards, okay? So notice that you have actually in this diagram, what's been shown is three different action-reaction pairs by Newton's third law. If he pulls hard enough, again, this vector will exceed the magnitude of this vector, and the sled along with him moves forward, okay? Okay, try this one. Okay, so a skier standing motionless on a patch of snow, holding onto a tow rope, the skier's mass, coefficient. Okay, what's the magnitude of the maximum force that the tow rope can apply to the skier without causing her to move? Well, that's the maximum value of mu sub s times her normal force, okay? So here's a diagram, kind of a free body diagram, okay? Her normal force is 579 newtons, so F sub s max is going to be 81 newtons in this case, okay? All right. There's a sled now and its rider moving at a speed of 4 meters per second. Try this one on your own before you see my solution. Okay, what's the displacement of the sled? It's getting more complicated. Okay, so here's my sort of semi-free body diagram. Initial velocity here, static or kinetic frictional force here because the sled. Actually, this is a skier. Sorry. Okay, I guess I drew that wrong. Anyway, skier, same physics, okay? So here's my SUBOT table, okay? I have that the acceleration of the skier, or the sled and its rider, is 0.491 meters per second squared, okay? All right. Now, using the third equation of kinematics, I can clearly figure out that the displacement of the sled, or the skier in this case, is 16 meters. Now, I want to make a note about the negative sign. It's negative since f sub k acts in the negative direction, but we know that the physics of the situation, especially if you draw a diagram, that the displacement of the sled is then positive, okay? And that's the case, all right? Now, on an incline, it can get more complicated. So what we're going to do is we're going to go back to the picture of this poor little dog on a ramp, and we're going to put vectors all over this little dog. Don't worry, no dogs were hurt in the production of this video, okay? All right, remember that 0 is less than or equal to f sub s, which is less than or equal to mu sub s times f sub n, okay? The dog is not moving, so this is the version of this equation that we are going to use in this situation. Now, note that also, if this angle is theta, this angle is also theta, and I've drawn the dog's weight vector acting directly downwards. Now, in this case, okay, and in all cases of things inclined on planes that are not moving, the magnitude of the frictional force, static frictional force acting upwards is equal to the horizontal component of the weight acting down the ramp, okay? Now, as I pointed out before, the vertical component of the weight with respect to the coordinate system with respect to the ramp is exactly equal in magnitude to the normal force of the dog acting outwards perpendicularly to the surface of the ramp. If it's tilted slowly upwards as theta increases, at some point the dog will slip down the ramp. As theta increases, f sub s increases until it can no longer hold the dog and it slips, in which case, when the dog slips, it's now kinetic friction that takes over, which is a constant, okay? All right? Okay, at this point, f sub k takes over. Just drawing a few other lines on this diagram to kind of make everything nice and neat and tidy geometrically. Notice that I have this vector right here, which I've superimposed up here, the static frictional force, okay? Notice that the vector sum of f sub n and f sub s, the vector sum of that is exactly equal to negative the weight of the dog. Okay, and we'll do some fun things with tilting blocks and planes and vernier probes in class, okay? All right, this example should look familiar to you. We're going to work through this again, and I'm going to add a few more things to it. Go ahead and read it to jog your memory. Okay, all right, the crate is at rest and not sliding. Here's my diagram of my vectors, okay? Turns out that W sub x, which is the force that pulls it down the plane, is 15.7, and since 15.7 is less than 21, the box is not sliding, okay? So we've done this one in class. You did this one in a test, okay? I'm adding a few more vectors here than we talked about in your test, but it's the same problem, okay? In this case, this is also the same problem that you did. Okay, the plane is tilted further upwards as indicated. Okay, so theta increases, then theta increases here. Notice what happens to the normal force as theta is increased. The normal force will what? The normal force will decrease because the W sub y, the vertical component of the weight vector, itself decreases. Okay? So again, W sub y decreases, the normal force decreases, the static frictional force, which is equal to, this should be W sub x, that also increases. The weight, of course, always stays the same, and what happens is it slides when it reaches an angle of exactly 42 degrees.